Assalamu alaikum, students and fellow physics enthusiasts. Welcome back to Cert K Loves Physics and Chemistry tutorials. Today's episode is a recap of a double-slit light interference experiment, specifically computing the wavelength of the light used and the angle of the line from the slits to the second order dark fringe on the screen. So join me till the end of this video. Watch and learn. And here's the question. In a two-slit interference experiment, the distance between the slits is 0.370 millimeters, and the angle of the line from the slits to the m equals 4 bright region on the screen is 0.407 degrees. Find letter A, the wavelength of the light used, and letter B, the angle of the line from the slits to the m equals 2 dark region on the screen. We are given the distance between the slits equal to 0.370 millimeters or 3.70 times 10 to the negative 4 meters. The angle of the line from the slits to the fourth order fringe on the screen, theta, is given, all right, equal to 0.407 degrees. And our first target variable is the wavelength, lambda, of the light used in the experiment. And also, whereas to find the angle theta 2, right? So this is the angle formed by the line from the slits to the second order dark fringe formed on the screen. The wave coming from the slits interfere either constructively or destructively, depending on the difference in distances between the slits in the screen, more commonly known as the path difference. So in figure A, all right, we have a case when the path difference is 0. And what is seen on the screen is the brightest fringe or band, usually called the central bright fringe or bright band. In figure B, right, this is the case when the path difference is equal to lambda, right? So what is seen on the screen is another bright fringe or bright band, right? More commonly called the first order bright band or the first order maximum. And in figure C, we have a case when the path difference is a multiple of 1/2 lambda. All right. So if the path difference is 1/2 lambda, what's seen on the screen is a dark fringe, more commonly described as the zeroth order minimum or dark fringe. right? And that corresponds to m equals 0. If m is equal to 1, then we have a path difference that's equal to 3 halves lambda. But since m is equal to 1, we usually call it the first order dark fringe or the first order minimum. So the formula that relates the sine of the angle theta with the wavelength lambda in the separation distance of the slits is given here. Sine theta is equal to m times lambda divided by d, right? Um, this is the formula, okay, in describing constructive interference, the results of which are the what we call bright fringes, okay, projected on the screen. So in this equation, the value of m is an integer such as plus minus 1, plus minus 2, plus minus 3, and so on, right? And in question letter A, since what we are asked to determine is the wavelength lambda, so we just isolate, okay, the wavelength lambda from this equation and come up with the working formula for computing the wavelength lambda. That is, lambda equals sine of the angle theta times the separation distance of the slits, small letter d, and then divided by m. That is, lambda is equal to sine of the given angle theta, 0.407 degrees. And then that's multiplied by the separation distance, 3.70, times 10 to the negative 4 meters, and then divided by 4. Since what's referred to is the fourth order maximum or the fourth order bright fringe. So with the help of your cycle, okay, we get the value of lambda equal to 6.57 raised to the negative 7 power meter in 3 significant figures. When converted to nanometers, that is equal to 657 nanometers. In question letter B, we're talking about uh, the dark fringes, which are the results of the destructive interference, right? So the formula is sine theta equals quantity m plus 1 half times lambda over d. All right. So the number inside the parenthesis is such that the path difference is integral of 1 half lambda, right? So if m equals 0, that means the path difference is 1 half lambda. If m equals positive 1, right, then the path difference is 3 halves lambda, and so on and so forth, right? And if we substitute now the given quantities, we're, we are required to describe the angle for the second order minimum, in other words, the second order dark fringe. That means m is equal to 2, right? So the formula sine theta becomes quantity 2 plus 1 half lambda over d, or that is sine of the angle theta is equal to 2.5 times lambda, the same wavelength of light that we computed in part A, 6.57 raised to the negative 7 power meter. and then divided by the separation distance of the two slits, 3.70 raised to the negative 4 fourth power meter, right? So when we do our math, we find the sine of the angle theta equals 4.44 raised to the negative 3, right? The unit meter already cancels out. And to determine the value of the angle theta, we just get the inverse of the sine of the value 4.44 raised to the negative 3 power. Again, with the help of your cycle, we finally arrive at the value of the angle theta equal to 0.254 degrees in 3 significant figures. This is the angle theta that is formed by the line from the slit, all right, to the second order dark fringe formed on the screen. And that's it. We're done. Until the next episode, mabuhay, mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.